Next three classes Atharva will take on his fiber photometry. After three classes, I'll start with actual EEG data analysis.
Uh, okay,
Yeah.
because I do not have any background in the biology, so
Oh,
I mean, I can understand very little from the discussion wherever the biological concepts are involved.
okay.
But I would be very much interested in knowing that once the data set is given, then how to analyze the data and develop the prediction models, etc.
Sure, sure. Yeah, we will come there. It will take a bit of time. So first class we'll deal with like whatever we learn from signal processing. We will try to implement that on EEG signals. So that will take one class, and then we'll like learn simple models through the data, like simple classification and of that sort on EEG.
Okay, okay.
Yeah.
After 3 4 classes, is it?
Yeah, after three, four classes, because next three classes Atharva will be taking. So he will teach fiber photometry and some some pre-processing steps, etc., with his notebooks, and then I will shift to EEG.
All right, yeah.
Yeah,
Thanks.
yeah, yeah, sure. We'll start in like a few minutes, maybe in another 5 minutes. Okay, we'll get started. So, is my screen visible, everyone?
Yes, visible.
Okay, cool. So, yeah. In the last class, we have seen basic signal operations such as flip of a signal, scaling, shifting, both in x and y axis. So I have shown a demo in a website called Desmos. I'll share the link where you can, simulate any mathematical formulation of a signal and see how visualize how it varies very easily with just few sliders. So then we have seen what are periodical signals, how they are represented using the time period parameter called capital T that we discussed last time. And also we discussed two standard periodical signals which are also called canonical periodic signals, which are the sinusoid and the complex exponential. And we have seen a proof of y e power j theta, the complex exponential, is equal to cos theta plus j sin theta. So it comes through Taylor series expansion, and we have also seen its geometric interpretations in a 2D coordinate system. And we have seen how a general sinusoid, that is a sine omega t plus 5, can be represented as a sum of sine and cosine. So this is equal to a1 sine omega t plus a2 cos omega t. So we have seen this, and this is called in phase component, and this is called quadrature component. So one second. Yes. And then we have seen different types of yeah, Fourier series, the trigonometric and exponential Fourier series, and how trigonometric and exponential are related with each other, how the coefficients are related. We'll see the equation once again before starting, and then we stop with how we can derive Fourier transform for an aperiodic signal from Fourier series. So whatever we taught in the last class is about mainly about periodic signals and how it can be represented via Fourier series. And these are all other concepts which are useful in later stages or right now when I derive other proofs. So this is a recap of the last lecture. So we'll start with today's lecture now. So just to revise the Fourier series equation, any periodic signal x with period t. So we generally represent a periodic signal with time period t has this. That means the same signal repeats every t seconds it repeats. So any periodic signal can be represented as sum of sines and cosines as shown in this equation, where there is a constant term, then a cosine term, then a sine term, and summation over multiple these are also called harmonics. N is called harmonics, n omega naught. So omega naught is called fundamental frequency, and n, as you increase n, it goes to first harmonic. N equal to 1 implies n equal to 1, and so on so forth. First harmonic, second harmonic, etc. N equal to 2 actually. N equal to 2 is called first harmonic because 1 is the fundamental frequency. So this is a essential expression of Fourier series, and then each of these coefficients can be derived in this form, where a naught is nothing but the average value of the signal, and an is nothing but average value of the signal when you multiply the signal with a cos of some frequency here, n omega naught, and similarly bn. So This is the equation for Fourier series for trigonometric Fourier series. But also you can express, we have seen there are two types of canonical periodic signals. One is sines and cosines, which are sinusoids. Another one is complex exponential. So you can represent a Fourier series in terms of complex exponential as shown in the next slide. Okay. Sorry. Yeah. Give me 2 minutes. There is some delay. Oh my god. But the moment it changes, I okay, fine. So basically in exponential series, I will speak, and when it comes you can see. So yeah, great. So this is called exponential Fourier series, where any periodic signal similar to the previous one can be represented as sum of complex exponentials with the coefficient here Cn, and e power j n omega naught is the complex exponential here. So and similar to the previous equation, you see Cn can be nothing but integral, which is the average of the signal after multiplying with the complex exponential, actually a negative of the complex exponential. So we are not going into derivation of these coefficients, but it is easy to derive. I will send a send notes so that you can see how the proof comes, but for now you just remember the coefficient is represented by this equation, and this is in general called synthesis equation, the first line here you see, because we are trying to synthesize the periodic signal x of t by summing all the complex exponentials here. And the second part is called analysis equation. Why? Because we are trying to know what amount of particular frequency is present in a signal. So this Cn says Cn amount of n omega naught frequency is present in the following periodic signal. So this is called analysis equation, and we have also seen relation between this an and bn are trigonometric Fourier series coefficients, and Cn is the exponential Fourier series coefficients, and you see a relation between them, which can also be easily, like, just by equating two equations and trying to find what is a common between Cn and a and bn, you will get this form of equation. So basically these two are same, but this is a more compact representation of a Fourier series equation. Okay. So is everyone clear with Fourier series equation, or did I go too fast? If you don't remember or ask, if you have any doubts, you can please ask. Okay, cool. So now we are like good to go with Fourier series equation, and now we'll see how a periodic signal, which is not periodic, is called a periodic signal, can be represented using Fourier transform, and how can we derive the Fourier transform expression using this Fourier series. Okay. So last class we discussed, but it went by a little fast, so we'll just discuss in detail a little more. So this is a demo that we saw, like as you increase the coefficient, how you see the more approximation of the original signal has increased more and more Fourier series coefficient. So okay. Okay, cool. So Here, let's say we have an aperiodic signal shown in this way. This is the signal of our interest now. And to find the Fourier transform or the frequency information of this signal, what we do is, this is a proof for it, so that it becomes more intuitive of how we know how the expression came up. So now what we do is, this signal x of t, we extend it has like virtually, it is like hack we do by extending this, by repeating the same pattern periodically over time as shown here, we get a periodic version of this signal. Okay, so everyone understood this. We are just extending from here, we are just repeating the same replicas of the same signal over multiple, at every t, basically at every time period t. Okay, and we call this signal x tilde of t. Okay, now since it's a periodic signal, we have a Fourier series for it. As seen in the last expression, in the exponential Fourier series, we get a periodic signal x tilde of t has summation of complex exponentials e power j n omega naught t. Okay, now we have expression for this coefficient. So basically we want to find frequency information, right? So from Fourier series we know Cn is the amount of a particular frequency n omega naught that is present. So we need to find Cn. So from here we go to Cn. Cn expression is straightforward from the previous slide. So it's nothing but 1 by t integral of x tilde of t, the periodic signal, multiplied with the complex negative of complex exponential, and we integrate over the time period t by 2. So basically I'm taking period t, let's say this is from minus t by 2 to t by 2, and everything go, let's say that is the period, the t is the period, the whole length of that. And so now what we do is, we have this expression, I'm just bringing this t on this side, so it becomes t times Cn equal to on the whatever is on the right hand side. Now what trick we do is, we try to extend the period t into infinite, so that you are left with the same signal x of t which we began with, and we apply this limit, that is, as t tends to infinity, how does this expression change? Is everyone clear until this point, until this 4 points? Okay, cool. I want to see all, like if you don't understand, please ask the question, because if you don't understand this, you'll not be able to follow the next slide. So basic idea here is, we have a x of t signal here, we are extending it to a periodic version here, and a periodic signal has a Fourier series. We write down the Fourier series expression and get the coefficient out, and from the coefficient now we try to see as t tends to infinity, because as time period tends to infinity, this you can see on the right hand side, this stretches to infinite, then you're left with the same signal x of t. So that's the idea. And we also know that omega naught, the fundamental frequency, is represented by 2 pi by t. Okay, so now we have t times Cn is equal to integral minus t by 2 to t by 2 x of x tilde of t e power minus j n omega naught t dt. This is the expression we have from 3. This is from third equation in the previous slide. Now as t tends to infinity, what happens? As t tends to infinity, the limits, the t here goes to minus infinity to infinity, right? And we also said that as t expands, that is tends to infinity, the x tilde of t, the periodic version returns back to the x of t, and then e power, let's say j n omega naught. So what happens to n omega naught? We know that omega naught is 2 pi by t. So basically if you draw an axis of 0, omega naught, 2 omega naught, so on, it goes some k omega naught, n omega naught, let's say, to the end. So this can also be expressed as 0, 2 pi by t, 4 pi by t, so on so forth, and 2 pi by t. So here if you see clearly, as t tends to infinity, these points, these neighboring points, come closer and closer because it is in the denominator. So what happens is it becomes more continuous. Therefore this all omega becomes a continuous axis instead of a discrete axis. Okay, so as t tends to infinity and omega naught tends to omega, a continuous variable, and dt will be same. So and let's tcn, let's replace with another notation just for simplicity, because it will, if you are integrating across time from minus infinity to infinity, it will be a function of only one variable, that is omega, because you are integrating across time. So let's say x of j omega is a function. So basically this is called the Fourier transform now. Okay, so this is the expression for the Fourier transform. Is everyone clear until this point how we got this expression for so now what we can do is, for any signal we can derive x of j omega, which is nothing but the frequency information as a function of omega. Now omega you can replace by 2 pi f. Omega is usually equal to 2 pi, it is equal to 2 pi f. So whether I say it's a function of omega or f, it is same. So this gives you the spectrum, and you can also represent this as x of f. So from this equation you can calculate the frequency information of a given signal. Okay, so reiterating the expression here, x of t is any signal, we have its Fourier transform, which is integral of minus infinity to infinity signal times the complex exponential e power minus j omega t and dt. So this is the Fourier transform. Until this point everyone is clear? If anyone has any doubts, please ask, or if you're not clear with the derivation. Cool, I see only one thumbs up. Cool. Okay, fine. So also this is an invertible transform. It's not, it is reversible basically. So once you have an x of t, you convert into its frequency domain by using this transform. From the transform you can always derive the signal x of t. And how do we do that? There is an expression for that here. We can derive this expression also, I will show in a bit. It is very simple. So it is nothing but x of t is 1 by 2 pi a factor 1 by 2 pi times the integral of the frequency domain information x of j omega and the complex exponential with a positive sign. So this is a positive sign, and you're integrating across omega because you want a function of time. So this is an inverse Fourier transform. So if you have a frequency information, you can always convert back to time. If you have time information, you can always go back to the frequency information. So essentially the key takeaway here is x of t and x of f are nothing but it's the same information. It's just the what we are seeing is different, but it's the same thing end of the day. So how do we get this inverse Fourier transform? Okay, so yeah, alright, this keeps moving. So I'll start explaining so that it will reach there. So yeah, so we have x tilde of t, that is a periodic version of the signal, can always be expressed as Fourier series like this. But now as t tends to infinity, what happens is what we want, same thing as what we did previously. For this is for inverse Fourier transform. So as t tends to infinity, omega naught tends to be small, it tends to d omega. So we have seen that in the axis omega naught is 2 pi by t. As t tends to infinity, the omega naught becomes smaller and smaller, and n omega naught becomes omega, a continuous variable. And here we are summing across n equal to minus infinity to infinity. But here now it is a uh, it's a continuous signal here. So n will be replaced by t, and minus infinity to infinity. We have Cn. Cn is nothing but wait, give me a second. Yeah. Now we have seen Cn is nothing but x of j omega, and we have Tcn is equal to x of j omega, right, from the previous equation. So what we get is it will be 1 by t here, right? And e power j, n omega will tend to omega, t will be same, and what will happen here is now we can replace t, 2 pi by t is omega naught, right? So what is t? T is 2 pi by omega naught. So if you replace t by 2 pi by omega naught, what you get is this becomes 2 pi, and numerator goes on omega naught. If you get omega naught inside, and omega naught has the time period tends to infinite, the omega naught tends to infinitesimal, that is a very small amount, which is denoted by d omega. So this is how we get the inverse Fourier transform equation. So is everyone clear with the inverse Fourier transform also? So it's the same thing we follow, we just tend t to infinite. Okay, cool. So basic key takeaway from all of this what we did just now is nothing but to find a Fourier transform of a aperiodic signal, we have to construct a periodic version of the aperiodic signal by making replicas of the same signal for every time period t, and then for that we have a Fourier series. From Fourier series we can tend the time period to infinite and get the expression of Fourier transform. So that's the key takeaway here. Okay, fine. So until this point, any doubts, please ask, or any comments, or if you didn't understand any part, please ask. Okay. So now we will look into some of the standard signals Fourier transform. So let's take, these are standard signals. I am not going to derive them. I will just show the integral expression and then show this. So I can send you the proofs later offline so that we can save some time here. So basically we are looking at a signal called rectangular pulse or rectangular signal. Basically, as the name suggests, it's nothing but a rectangle in some time period minus t1 to t1. Okay, and it is usually denoted by rect of t1. T1 denotes how what is the span, like how much, what's the width of this pulse. Okay, so for this signal we can also represent it as x of t equal to 1 in the interval t1 minus t1 to t1, which is denoted by mod of t less than t1, and 0 in the remaining places. So this is the mathematical definition of a rectangular pulse. Now if we take a Fourier transform of it, we get one special type of a function or a spectrum, here spectrum, because we are taking time domain to frequency domain. So when you integrate minus t1 to t1 and this complex exponential, you get a function called sinc function. So this is a form of sinc function. So this becomes a very important function because most of the theory of sampling the signal, any continuous signal to digital form, and all are dependent on this sinc function, because every sample is like a small rectangle. So each rectangle will be in the Fourier domain, it will be a sinc function. So how does this function look here? So this function looks this way. So you have increasing this. So basically it is nothing but 1 by omega sine omega t 1 scaled by 1 by omega. So as it goes to infinite, it decays, you can see here, and it's a sinusoid. And can anyone tell where we can find the zeros here on this? Like, what are these points on this omega axis? So basically we want
Is it 2 pi by t1? Is it?
correct, yes. So has someone pointed in the audience? I think we know it, right? Yes.
Yes.
Yeah. So when you equate omega t1 to 2 and pi, the sign becomes 0, right? So basically you will get omega is equal to 2 and pi by t1. So all this occur at multiples of 2 pi by t. 2 pi by t. This will come at next multiple, the 4 pi by t, and so on so forth. Okay. So this is called a sinc function. Now we will see a trick to, when you see a rectangle, how to know its Fourier domain part very quickly. So it is a sinc function that we know now, but how to exactly know the width and the time period t, etc. of this function. So okay, so here is a, okay, I think, yeah, now it came. So this is a general rectangle where we have a rectangle of amplitude a and extending from minus t by 2 to t by 2, right? Now what is the Fourier transform of this, if I ask? So there is a quick trick to memorize or just put down the equation. So what we do is we take the area of this. What is the area of this curve, area of this rectangle? Can anyone in the audience tell? So basically the width is t and the height of this is a. So
AT.
yes, right. So basically we have that has the the scaling part here on y-axis, which is 80. So this is the area of the rectangle function, and there is a function, let's say there is a function called SA function. It's also called sampling function. We'll get to know why it is called SA function or sample function. And what we do is, you see this axis, right? This is t by 2. So that t by 2 comes here, and the frequency variable comes as omega. So basically a Fourier transform of this is basically the x of j omega for this rectangle signal. So nothing but area times SA function of the frequency variable times the half period of this rectangle. Okay. So a SA function also looks exactly like a sinc function. It is a sinc function just with some scaling factor. So what is a sinc function? A sinc function is nothing but a sinc of theta or sinc of x is nothing but sine of pi theta by pi theta. So this is the sinc function expression, and it looks the same way that we saw. Okay, and zeros at multiples of this. So yeah, so this is a sinc function, and SA function also looks same, just that the pi factor is missing here. SA function of theta is nothing but sine theta by theta. Okay, so now you can always replace omega by 2 pi by t and 2 pi f and calculate in terms of f also. So it becomes SA function of 2 pi f, omega is 2 pi f and t by 2, something of that sort, and you cancel the factor 2 because it is on numerator and denominator, and you get SA function of pi f t 8. So now you can see this is not if you have a pi factor in this, saw of pi t is nothing but at sinc of ft. So basically you get this expression. You can either represent it in sinc or saw function. So this is a Fourier transform of a general rectangle. Okay, this will be very useful and becomes very handy if you remember this rectangle, because rectangle is one of the common signal for understanding sampling or low pass filtering, etc. Is everyone clear with the general rectangle Fourier transform? Cool.
Will you also show when what happens when you change the sampling frequency? Or
Yeah, I'll show them later, because right now yeah, I can show them.
Deepak, could you go to the last slide?
Yeah.
means what does this Fourier transform depend on? Like, will it always be the same, or does it depend on some signal? Amplitude, it will depend. The time, it will depend,
so
but some other factors.
this comes handy when I'll come later. I have that slide in like next two slides.
Okay.
So basically the real time, so whatever Fourier transform is defined in the limits minus infinity to infinity. The assumption there is signal is of infinite length, but in real world signals are of, you can't get a signal of infinite length. There are always finite length. So what happens there is the signal is always multiplied by a rectangle. So because of this finite length, we call it's a spectrum estimation, but not or not exact Fourier transform. It's called approximate or almost Fourier transform. So there, like, we will know how a real spectrum differs from the snipped spectrum using this sampling function or sinc function, and the same thing can also be applied for sampling. I'll show that when I come to the impulse train. So yeah, Vinod, you have some doubt?
Yeah, I got it. I just was confused in how can you write it as sinc ft, but I got it.
Yeah, you just replace this, you get a pi factor, which is nothing but this saw function of pi t is nothing but sinc pi theta. Yeah, okay, great. So we have another it's not a realistic signal, but it's called an impulse or Dirac delta function. It is nothing but a function at 0 having area equal to 1, and it is depicted by showing as a arrow mark at the 0. So this is called a Dirac delta function, and its area is equal to 1 at 0, right? And its Fourier transform is nothing but you write the expression of it, what we have seen, and usually any function, so since it is defined only at 0, any function x of t, when you multiply it with the Dirac delta function delta t, it is nothing but delta t times the signal's value at 0. Okay, so x of t is getting confused here. Let's say some f of t. Okay, so if you multiply any signal with an Dirac delta function, it is nothing but Dirac delta function times 0, because it's a area, it has an area, it doesn't have a definite value at 0, it's the area is 1. So therefore this is one of the identity that we have from the definition of Dirac delta function. And when you use this definition here, you will see that the area, the expression reduces to 1. So basically Dirac delta function's Fourier transform is nothing but it's a constant 1. Okay, so this is Fourier transform of Dirac delta function. This is the Fourier transform. This is omega axis or frequency axis, and at any frequency you see a constant value of 1 when you take a Fourier transform of this Dirac delta function.
Shouldn't it be like it is a very, very high frequency change? No, which happened once.
So this is a special case of signal. This is not like a step function. If you're talking about a step function, then it comes like that. But
It is infinite.
yeah. So this has a uniform amplitude at every frequency. So it has every frequency of same power. So this is a unrealistic signal. This doesn't exist. So what we do is in real in real world, what exists is we replace this delta with a small and narrow rectangle. So that is where the sinc function becomes the sampling function, because you can't have a real time Dirac delta function. So we generate a narrow rectangle and that becomes the sampling function. So usually we use Dirac delta to represent sampling theoretically, but when we are doing practically, we replace Dirac delta with a rectangle function. So basically you have the Dirac delta, the sinc function, but when you narrow to the like maximum extent possible, you get this Dirac delta function, and that sinc function just goes flat when you compress it to this form. And remember, it doesn't take any finite amplitude value here. It's the area is 1, so it just goes to some extent. We just represent it like this. So it is not exactly like a sharp shift and you see a high frequency component. So okay, so this comes handy later. I'll show the impulse train and all. So just bear with another Fourier transform and then we'll see. So this is a slight trick of we have been talking about Fourier transform of a aperiodic signal, but and Fourier series of a periodic signal, but also we can get a since Fourier transform is a kind of operation, so we can operate the same on periodic signal also. So let's if I ask what is the Fourier transform of a sinusoid, how do you say it? So for that there is a reverse trick. What we do is, let's take a signal with Dirac delta here. This is a Dirac delta function. Let's say x of j omega, we have this one. So what does this say? The Dirac delta is centered at omega naught. So you have this thing, and at omega naught you have a Dirac delta. So, and this is omega, and this is let's say amplitude of it. So this is 2 pi times of that. The area is 2 pi basically. So let's say we take a signal with this as Fourier transform, and now we try to do an inverse Fourier transform on this. So when we do an inverse Fourier transform, what you get is 1 by 2 pi integral minus, we have derived this inverse Fourier transform expression. So when you do this, as we have seen, when you multiply a Dirac delta with a function, you get Dirac delta times the function value at omega naught, because here the Dirac delta is shifted to omega naught. So basically when you evaluate this expression, you get a complex exponential e power j omega naught, which is nothing but our standard canonical periodic signal, complex exponential periodic signal. So now if you take sine, right, sine is nothing but e power j omega plus e power minus j omega naught t. So if you do this, you get this. So you get a 2 impulse at minus omega naught. Actually you'll have a negative, sine will be a negative of this by 2. This is the sine function. So sorry, yeah, this will be actually a negative. Yeah, you will have a omega naught at minus omega naught, you'll have this. So basically this is the Fourier transform of sine omega naught, sine n omega naught t basically, right? So is this clear, what is a Fourier transform of a periodic signal? So basically it is nothing but it's a monotonic signal. It has one frequency omega naught. Then in frequency domain it will have impulse, the impulse or direct delta at that frequency value omega naught. So yeah, so basically if you have a monotonic signal, you will have a direct delta at that point. Okay, so also now coming to we have seen one single impulse, but we can also create a train of impulses. So that is shown as this signal. So at every time, at every t, you will have one impulse function. Okay, so on and so forth. Okay, now what is a Fourier transform of this impulse function? So there is a way to derive it. Right now I will not go there. So you might be thinking at 0 you have impulse, it will be 1, but this is slightly different. So when you actually derive through Fourier transform expression, you get the Fourier transform. This is omega or f. You get a impulse train in the Fourier transform also in the frequency domain, and where the impulses will be there. So at 0, at reciprocal of the time period of impulse train. Here at t there is an impulse, here it will be at 1 by t, 2 by t, n by t, so on so forth. Okay, this is the Fourier transform of impulse train. So basically this is also periodic signal. So if you convert any periodic signal into Fourier series, you will have sines and cosines, and sines and cosines Fourier transform will again be impulse at that frequency, right? So based on that logic, you will get impulse train Fourier transform is impulse train, just that the impulses are at reciprocals of the times at which the impulse are there, or the direct deltas are there. So is Fourier transform of impulse train clear?
And this sort of the still 1, right? The amplitude is still 1 in both cases.
So direct delta doesn't have amplitude, so it is just area is 1. So yeah.
You
So
can
that is why
probably show it using like a notebook by adding sine omega 0, sine 1 by 2 omega 0. Like as you add terms, it is more and more closer to that impulse train. Can you do that?
for the Fourier series you are saying?
Yes.
Yeah, I have shown that in the last class, but I can show again.
Oh, okay. I wasn't interested.
Okay, I can show one. I can show that. But yeah, I have a video of that also. So these are the videos.
Oh, okay.
So I have shown in the last class where we try to do the same thing in the notebook. So as you increase the coefficients, it becomes more and more rectangular pulse here. So, and similarly you can see for other signals also. If you see a double tooth sawtooth signal like this, you see this one. And also, just to reiterate, we have seen even odd functions. So since this is only even, this signal, so we get only the bn coefficients and not the an coefficient. And similarly, this is the even function, so we have only an coefficients but not bn, which are zeros. And same goes with this signal as well. Okay, so actually I haven't
Deepak, so
yeah.
So I think this was just the last slide where you showed that sine omega t in frequency domain can be just sort of two impulses at omega naught and minus omega naught.
Correct. Okay. Yeah, this one, right? Yes.
Right. So in the time domain, it is sine omega naught t, but in frequency domain, it is kind of subtraction of these two, e to the j omega naught. And so, like, how do we make it on a graph?
Okay, so basically sine omega
In
naught
frequency
is a
domain.
real signal. So So when you expand this e power j omega naught t in Euler's representation, cos omega naught t plus j sine omega naught t, and you have e power minus j omega naught t, which is nothing but cos omega naught t minus j sine omega naught t, right? So basically you're replacing omega naught with minus omega naught, and since sine is an odd function, you get
Right.
minus out of it, and cos is even function, so it remains same. So basically when you subtract these two signals, you will, and you divide by basically 2j actually, so 1 by 2j times e power j omega naught t minus e power minus j omega naught t, you will this will be equal to the sine omega naught t function.
Right. So in frequency domain, it's in time domain it is just a sinusoid, right? Sine
Yeah,
omega
just
naught
a
t with a
sinusoid.
frequency omega naught.
Yes, yes.
But how does it look like in the frequency domain? Where are those spikes?
Yeah, the spikes are at the frequency value omega naught. So if the sine is at 2000 hertz, you'll get peaks at 2000 in the frequency domain, plus 2000 minus 2000. So usually negative frequency don't exist, but when you do it theoretically, they come up this way, and so yeah.
So one is a positive impulse at omega naught, and another is a negative impulse at minus omega naught.
Correct. Yes. So if you take cos,
Is that correct?
Yeah. If you take cos, you will have two impulses on the same side of y-axis. You'll have two positive impulses at omega naught and minus omega naught. So it's nothing but
Right.
you are adding these two complex exponentials, positive and negative complex exponential. You get that. So basically, impulse don't exist in real time, and infinite sinusoids don't exist. So when you do in a computer, when you do a Fourier transform of sinusoid, you don't get an impulse because impulse is unrealistic. So we'll see how a real spectrum of any signal looks like in a bit. Yeah, cool. Okay. So now coming to what I have been saying, any more doubts until the last slide? Okay, so basically I have been saying this, repeated this 2 times. So basically we, for a given signal, we estimate a spectrum. We don't get an exact spectrum. So why do we not get an exact spectrum? Because let's say this is some signal with like infinite duration. So for this signal, you can get an exact Fourier transform because the limits are full, like minus infinity to infinity. But in real world, they don't exist. You will have, like, you have access only to a snippet of this signal. So basically in this red window what I'm showing, you have only this signal. So I'm not drawing exactly, but yeah. So this part of the signal only you have, and on this you do a Fourier transform, right? So if you do a Fourier transform of infinite version, you get exact spectrum. If you do on a snipped version, you get a approximate spectrum. Why is it happening? So you can think of this infinite signal. This signal is being multiplied with the rectangular signal in this time period. So you have a rectangle in this time period, and basically you're multiplying this infinite length signal with this to get a snippet of that signal, right? So after getting snippet, you do a Fourier transform. So how does that Fourier transform look like? So there is one theorem called convolution theorem. I'll get into what is a convolution operation. So what is the convolution theorem? If you multiply in time domain, in frequency domain, it's a convolution. We'll get into how a convolution operation looks like, and the other way also goes around in convolution in frequency domain. Similarly, if you convolve in time domain, you get a multiplication in frequency domain. So basically here we are multiplying with a rectangle. So what happens in the Fourier transform is you'll have the sinc function. Basically square a rectangular pulse Fourier transform is a sinc function, right? Sinc function convert with the spectrum of the actual signal x of t, and you have only the let's denote this as x cap of t. So x cap of t is nothing but x of t multiplied by rectangular function of whatever time period of your interest. Okay, so basically this is a signal, and since we are multiplying, it will be a convolution. We'll get into what is a convolution operation in a bit. So basically it will not be the exact spectrum that we discussed until now, the way we derived by using the expression integral minus infinity to infinity. So is it clear why we call for a given signal we estimate a spectrum and not actual spectrum? Any doubts here of what I told, except for what is convolution operation?
So you're saying the Fourier transform of x cap t will be just a sinc function of that time period and the Fourier transform of the signal. What is that
No,
spectrum?
It's a convolution of that. It's a convolution between the spectrum of this signal, this is x of t, and the sinc function, which is the Fourier transform of the rectangle. So it's a convolution operation. It's some operation like addition, subtraction, multiplication. Convolution is also another operation. Okay. So
what is the spectrum function of xt? Like, what do you mean by spectrum function?
oh, it's just the Fourier transform of this signal x of t. So basically it will be
Okay.
x of j omega or x of f. Okay. Okay, fine. So I'll show this a convolution operation. What happens in a convolution operation is we have two signals, or two either time or frequency domain, two functions. Let's say let's not mix with signal and frequency. So we have two functions of this shape. Let's say one is triangle and one is, okay, let's take these two signals. One is this and one is this signal. So let's say 1 and 2 signals. So what is a convolution operation? You take you flip the signal 2. So basically you flip it, then it results in this. It's a flipped one, and you have a triangle, and you start shifting the flipped version in time. Let's say here will take time, so you shift in time, and as it overlaps you multiply and you get the area of that curve. Overlap, multiply, area under the curve. So that is the convolution operation. So basically the red dot is moving, right? The red dot shows the area value under this overlap when you flip and start moving the signal, and as it moves you try to plot the area value. So this is the convolution operation. Okay, so
Could you repeat once more, please?
yeah, so basically you have two signals. One is triangle like this. Give me a minute, I'll just clear. Okay, fine. Okay, so basically you have two signals. One is a square, this is the first signal, let's say, and let's denote this as f of t, f1 of t and f2 of t. f2 of t is a sudden exponential decay. So suddenly you get an exponential and it decays. Okay, these are the two signals. what you do is you flip the signal f2 of t by flip and shift it to the end as much as possible. So how is it shown? T minus tau, let's say, and this is f1 of tau. Just replace t by tau here for the sake of convenience. Okay, so you're shifting the signal and starting to overlap, multiply, and whatever like as you shift, you find the overlapping area, and that area you show it here. If you see this one, so right now there is no overlap area, so it is always 0. Once the overlap starts, it starts increasing, and that area value is what you are trying to plot here. As the area of overlap increases, you see it increases, and when it reaches the peak and starts moving down, the area also decreases, and therefore the function decreases. So this is basically the visualization of convolution operation. So it is denoted by f integral f minus infinity to infinity f1 of tau, f2 of t minus tau d tau. So if you get, this is nothing but f1 convolution f2, and so it is hard to visualize in terms of formula, so I put this video. So yeah, is it clear, the convolution operation? So you can either convolve in time or frequency domain. Okay, so give me 2 minutes. I think this is a bit of I think this will be a bit complex because I haven't thought the. So basically here what I'm showing is in the frequency domain, wait, let me stop this. So you have a Gaussian function here, Gaussian kind of function. So I didn't discuss the Fourier transform of a Gaussian function. So a Fourier transform of a Gaussian function is nothing but Gaussian itself. So I will send some of the equations and visualizations of Fourier transform of very standard functions. And for a square rectangle function, we have seen it's a sinc function, which is shown in green here. So basically what we are doing is a rectangle in frequency domain, the corresponding time domain of a rectangle in frequency domain is again a sinc function. So basically what when you do a low pass of a signal, what you do is a low pass filter is defined by this rectangle as shown in frequency domain. So in time domain it is a sinc function. So when you multiply in frequency domain, when you multiply a rectangle with any spectrum, let's say x of f times rectangle of f, so this is nothing but low pass filtering operation, right? Sorry, multiply.
Isn't this time domain and frequency domain interchanged?
Yeah, in this example it is interchanged, but in when you do low pass filter, you do in frequency domain, right? So yeah, this is just to give an intuition of what happens in time and frequency.
Means these titles are interchanged, right?
No, it is right only for this example. It is right, but when you link with what I explained and this, then it is reversed. So basically a low pass filter is nothing but it cuts off, let's say this is
frequency.
This is 0, and let's say fc is a cutoff frequency. So basically it has to cut off some frequencies beyond fc. So basically there it will be 0 and here it will be 1. So this is frequency domain of a low pass filter. So basically they are low pass filtering this a Gaussian signal like this, which is shown here, a Gaussian in frequency domain, which is also a Gaussian in time domain. So right now you just remember a Gaussian remains Gaussian in time and frequency domain, just the axis differs because time and frequency are reciprocal to each other. So as long as it passes the whole Gaussian, there is no change in the red signal. There will be slight changes in the ends, but they are usually ignored. But as you decrease it, and if the cutoff frequency goes below the Gaussian, below the bandwidth of the Gaussian signal, you can see that there is a blue curve that appears here. So the blue one shows the, you know, after low pass filtering what is happening to the time domain signal. So right now you don't have to worry, this is for other class, but this is just to show time and frequency convolution. So basically if you multiply in frequency domain, it is convolution in time domain. And here we have seen previously, if you multiply a signal with rectangle, it is nothing but convolution of the spectrum of the signal with a sinc function, because sinc is the Fourier transform of rectangle. So is this clear, and why we call it as estimating spectrum, and what is the convolution operation? So cool. So coming to the previous examples that we were showing, we were writing, okay, so we have a 2 hertz and 3 hertz signal, and you sum up, you get this kind of a time signal, right? And we always used to write it as almost Fourier transform, and it's not an impulse, as we discussed in Fourier transform of a periodic signal, the sinusoid signal. So what exactly is happening is, this is not an infinite sinusoid, it is snipped until like few seconds here, maybe 2 seconds, yeah. So it's a snippet of the signal, which is nothing but the whole sinusoid multiplied by a rectangle. So when you do that, instead of impulse in Fourier transform, you get a sinc function like this, and at 2 hertz you get a sinc like this, and for this you get at 3 hertz, and when you sum up, you get at 2 hertz and 3 hertz signal. So basically for sinusoids, you can, you know, easily get a Fourier transform of any sinusoid or sum of sinusoids, etc. So is this clear now? Like how does the estimate of a sinusoid, spectrum estimate of a sinusoid look like? Cool.
I still didn't get that. How come this rectangular pulse in frequency domain look like that in the time domain?
Oh, how does it look? I mean, I haven't proved it, but when you actually derive and integrate the e power minus j omega naught, I'll send you the derivation. So when you integrate that in that expression using some transformation of variables and some integration techniques, you get a sinc function. So
That's
rectangle.
very weird.
Sorry.
It's like weird. Why should it change in time? But so this rectangular pulse is in time, right?
Yeah.
This
So
I understand.
I can tell you another.
No, this I understand.
Yeah. Okay. This
But
one
the
you're saying.
plot that you showed.
This one you're saying.
No, next the plot, the second last line. This one.
Oh, this one.
In this in frequency domain, it's rectangle, and in time domain, it is.
Yeah. So wait, I will just okay, just not look at this. This is a little confusing. So you have a rectangle, and you do a Fourier transform.
That I understand.
Yeah, this is in time domain, and in frequency domain you get a sinc function, right?
Yeah.
Similarly, now let's say you have in frequency you have a rectangle, and you do a inverse Fourier transform. So basically inverse Fourier transform and Fourier transform has similar integral expressions, right? Just the positive and negative sign of the complex exponential changes. So if you see that way, and this is the sinc is symmetric, so when you do inverse Fourier transform on
So time domain will get something like that.
yeah, time domain will be like a sinc signal.
Okay, and where does the convolution come in? Like I missed that. Sorry.
So convolution, okay. So what I was saying is, okay, I will actually draw.
Except convoluted with rectangular pulse.
So basically, one second. Yeah, we have some infinite signal usually. Like let's say this is extending to infinite, but in real world, we only have a snippet of this. So basically, a trimmed version of this only is available. We don't have like infinite signals don't exist. So if you want to snip a signal, what you would do is this signal x of t, let's say x of t, you multiply with the rectangle of this whatever the snippet length you want, right? So then what you get is this will result in a snippet of this signal, only this much, right? Now on this signal we want the Fourier transform of this signal. Instead of doing Fourier transform on this particular signal, instead of this, what we do is we take the Fourier transform of this, which is x of f, and Fourier transform of this, okay, which is nothing but the sinc function, sa omega t, right, whatever, a sinc function. And from the convolution theorem, we have that if you multiply two signals in time domain, in frequency domain it becomes a convolution. So basically, if you want Fourier transform of this one, you just convolve individual Fourier transforms, and this is a convolution.
Using this trick, you can
correct
find the Fourier transform of limited times.
Yeah, limited.
You just expand them infinite times and then
yes,
like that.
Yes, right, exactly.
Yeah, but the problem, Deepak, is that we don't know what capital X f is. Like the computation is not so simple, right? Because
yeah, that is true. That comes later when we deal with for FFT, DFT, and all. But we will not deal with that. We will just go with the intuition of Fourier transform right now. So as we teach, no, that time I can just parallelly show you instead of spending time on like how to derive signals for your transform. Okay. So similarly here, you are multiplying a sinusoid with a rectangle because it's a finite length sinusoid. That is what you have, and therefore instead of impulse, we have seen like a sinusoid, sine omega naught t. Fourier transform is nothing but an impulse at omega naught, right? So or f, whatever the frequency, f naught. Okay. So instead of impulse, what you have is impulse is convolved with a sinc function because rectangle's Fourier transform is sinc. So what happens when you convolve a sinc with an impulse? So whenever you convolve any signal with a Dirac delta function, you get that the sinc function at that Dirac delta point. So basically you get a sinc function here at omega naught. So this Dirac delta function has a special property that whenever you convolve a signal with it is very intuitive also because it's just one area is 1 at that point at 0, or if you have delta of omega minus omega naught, at omega naught you have area 1. So when you do a convolution operation, you get the whole signal at that position. So basically you get an sinc function at that frequency. So and if you sum many sinusoids, you get a multiple sinc function at those frequencies. So is this part clear until this?
So when we convolve with the Dirac delta function, we get the function itself. Is that correct?
Function itself at wherever the Dirac delta is. So for example, you have a Dirac delta at omega naught. Okay, omega naught. So this is nothing but delta of omega minus omega naught, right? Now if you convolve this with some signal x of t, you get the signal x of this will result in x of t minus, sorry, let's not confuse between time and frequency. So some value, some k, let's say k, t minus k, you will get x of t at k. So you'll end up with this, the signal at that position where the impulse is. Okay.
I thought it would be multiplied by.
Sorry.
Yeah. You're converting the Fourier transforms or the time domain? Time domain.
Yeah, I'm confusing a bit. So Either way you can do. So Fourier domain and time domain are just the domains.
But
So
if you do it in Fourier domain, then the Fourier transform of Dirac delta is constant.
yes, Fourier transform of direct delta is constant.
And then xt whatever Fourier
Yeah.
transform. So Fourier transform of xt will be multiplied by a constant amplitude.
Yeah. So
Everything will be scaled.
wait, 1 second. So we are just convolution in frequency is multiplication in time. So whatever you're saying comes in multiplication. So basically,
Okay.
yeah. If you do that, you get a multiplication of that. So the spectrum will remain same. It is
So the
yeah. So here we are convolving in like multiplying in time, but convolving in frequency. So we are convolving an impulse with the sinc function in the frequency domain, not in the time domain.
so convolving in frequency domain is multiplication in time domain.
Yes, correct.
So even if let's say I multiply, so I convolved Dirac delta and any function in frequency domain. So I will get what? I will get some amplitude multiplier basically. It's an amplitude
Correct,
multiplier
just
for all the frequency.
Yes. So basically it is
But
one node.
when I multiply Dirac delta with xt in time domain, it will be like 0 all time and then 1 again. Like it will be Dirac delta, right? Dirac delta multiplied with any xt is Dirac delta. Right?
Yeah, direct delta times the function value at that point where the direct delta is there. Correct.
So this doesn't match. Is there some?
I think you're getting confused between time and frequency domain. So we will discuss this maybe in the next class. I just want to show something and then
Okay.
come back. Yeah. So yeah, we can discuss offline or. So basically, if you multiply delta of t with x of t, what happens is this is called shifting property or delta of t minus t naught. You will have delta of t times x of t minus t naught. So we'll discuss this later, but yeah, right now we will not go into it. Just for this one, we are just doing. So we are multiplying sinusoid, infinite sinusoid with a rectangle. Therefore, in frequency domain, what happens is the sinusoid function Fourier transform is impulse direct delta at that frequency, and Fourier transform of rectangle is sinc function. You just multiply it and you get this value. Okay. Okay, fine. So how much time we are left with? Okay, fine. So we'll quickly go through this. So I just want to introduce this concept called frequency resolution. So what does this mean is how well you are able to differentiate between two frequencies for a given signal, right? So what does it depend on? So just now we discussed with estimating estimating the spectrum of a finite length signal or time limited signal. So signals are always time limited. So whatever you do is an estimation, and therefore this frequency resolution comes in picture because you have only finite length signal. You can't get the perfect Fourier transform, right? So what does it depend on? So basic thing here is the longer you observe a signal, the better frequency resolution you get. How did we come at this? It just depends on there are multiple ways to explain this, but since we are not dealing with the discrete Fourier transform or fast Fourier transform thing, we'll just get one type of intuition for this. So
Your voice is a little unclear. Could you move closer to mic or something?
Oh, is it now?
Yeah, much better.
Okay, cool. So basically, I am saying that we are discussing this concept called frequency resolution. So how well you can resolve two neighboring frequencies for a given signal. This concept comes into picture because uh, it's always a spectral estimate, because we only have time limited signals in real world. So the basic key takeaway that will be at the end of this slide is, the longer you observe the signal, the better is the frequency resolution. So where is it coming from? It comes from the sinc function only. So if you take the rectangle of width t, its Fourier transform will be is a sinc function, and the neighboring amplitudes will decay very quickly, because it is proportional to 1 by frequency. So, and what is the width of this main lobe? This is called main lobe. Width of the sinc function is nothing but it's a reciprocal of time, rectangular pulse width, right, minus 1 by t. So you have 2 by t, 3 by t, so on, all the nulls where it becomes 0. But right now you just focus on this main lobe width, right? And now if I narrow down this, what happens to the Fourier transform? So can anyone guess, based on what we discussed, if I narrow this t, what happens to its Fourier transform? So basically you'll get a sinc function. So what happens to this width of the main lobe? So t is reduced.
That should increase because t has
Yes,
decreased.
correct.
Yeah,
So
1 by t should increase.
yeah, basically it becomes wider and wider. So if you plot on this, it becomes a wide sinc. As you narrow down the width in time, the sinc function main lobe width increases. So basically, you can intuitively imagine that as I reduce the time, basically reduce the time window here. Time window is nothing but you are multiplying a signal with rectangle. So if I reduce the time window, the corresponding sinc will be wider. So that means the frequencies are getting smeared off to the other frequencies when it becomes wider, because you're convolving in frequency domain. So basically, the longer period you observe, the sharper is the sinc. The sharper is the sinc, the better is the frequency resolution. And when you cut short the signal within time, you get a wider and wider sinc function, and therefore there will be a leakage between frequencies, and you will not be able to resolve. So that is just the intuition. There are different ways to explain this frequency resolution, but for now this is a thing that you have to take home. So is it clear? Any doubts, or if I went too fast?
So this Fourier transform sort of becoming wider and wider. How does that translate to sort of low resolution?
Yeah, so basically when you're taking so we have discussed this one, right? You have a time limited signal. How do you get a time limited signal? By multiplying with a rectangle, right? So when you multiply a signal with rectangle in frequency domain, the Fourier transform gets convolved with the sinc function. So when you have a wider sinc, the leakage of that spectrum will be more to other frequencies. If you have when it is a wider rectangle, you'll have sharper sinc function. Therefore, the leakage will be less. But if you have a narrow rectangle, you'll have a wider sinc function, and therefore the leakage of the spectrum will go to other frequencies. So it will smear out if you have a narrow signal. So basically it's called time frequency trade-off. So if you observe a signal for longer, you have a better estimate of spectrum. If you observe for very short time, you have a very smeared spectrum. So that's the key here. So is it clear? Yeah, cool. I hope everyone is with me until this point. Okay, cool. So there are also better ways to estimate a spectrum. I will quickly go. I'll take another 10 minutes and I'll show one demo to the end. So a better way to estimate a spectrum is, let's say you have a signal and you have, let's say, first low frequencies and then it goes faster, 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 and again slower, slower. So now if I give this signal and ask you to take a Fourier transform, you get one estimate, right? So but that estimate will not be clear on at what time what what frequency is present. And so if I take this part and give it to the spectrum, you get a in the Fourier domain you see more power in the slower frequencies, in the smaller frequencies. When I take this and give, you get faster frequencies. But if I take whole thing and give, it will smear out this effect in time. So to not have this problem, what we do is and also this rectangle is a very sharp signal because it has, you can see the rings in the sink, right? So you can multiply by a smoother window. So what we do is we take a let's say Gaussian, or it's also called Welch window, one type of window. It's a smoother window. It has a like softer ends. You multiply that, you get one spectrum. Let's say you get some spectrum like this, and you take the other, you shift the window by a small amount and take this other spectrum, right?
So window means you are multiplying this particular signal to this, or you are...
Yes, multiplying, correct, exactly. So we are multiplying each snippet with a window and taking Fourier transform. So what we do is we take the multiple snippets of those by shifting that window, and you get multiple spectrums, multiple spectrums of this sort. And what you do is you take all of them and take an average. So that gives a better estimate of a spectrum than just taking the whole signal and estimating the spectrum. And this windows, the other advantage with Welch method is you have a smoother window. Therefore those the side transitions, the ringing effect, the rings here are not high because it's a square signal. The rings are high. But if you take a Gaussian signal or some smooth window, this ends will smoothen out. It will just be the Gaussian type of signal. So this is a better way to estimate spectrum of a signal. So for example, you're playing music, you have different frequencies coming in, and you want to estimate what is the spectral energy of particular music. Then you do this kind of thing so that you get better estimate of that spectrum instead of just taking the whole signal and doing the Fourier transform. So there is some resolution lost, but still you get a better estimate, better information of what frequency is present in a given signal. Okay. So if you extend
right, but
sorry.
Yeah, but doing this sort of tends to sort of penalize the endpoints and the beginning points, right? Because those are kind of at the tails of the Gaussian, and they are very small number you're multiplying by. So those number become almost
So
zero.
basically we don't take like discrete steps like this. We continuously stride it. We move very small amount and take it, so that when you average it out, the ends of end smooth and attenuation of the ends will go away when you average it out, because in one case that part is the attenuated part, but if you take some other window, it's not the attenuated part, it is on the peak part. So that way it will compensate. So yeah.
So do we take like a sliding window and then take the Fourier transform?
Correct,
and
correct. Not in discrete steps, but rather a continuous stride. We move very small amounts, like a slide, and then take it. Yeah. So that way you can remove this attenuation effects, because if you're just, your point is right, if you're just taking that, then the attenuation will cause artifacts in that spectrum or in the signals information. Yeah. Also, similar fashion, instead of averaging it, we can plot the same thing in a two-dimensional plane, right? you have this signal, let's say fast, slow, and it moves faster, faster, faster. So when you take this kind of a signal, you can take a small window, take a spectrum, and plot on y-axis. Let's say this is a frequency axis at a given time point. Let's say this time point is midpoint is, let's say 0 to t1. This is t1 by 2. At t1 by 2, you will plot a spectrum of this like this. Let's say the spectrum looks like this, for example. And similarly, you stride it, shift it, and plot in the next t1 plus some delta t by 2. You'll have another spectrum, right? So on and so forth. So what you will get is, here you'll get time, here you'll get frequency, and basically you're dividing this into multiple blocks.
Heat map.
Yeah, basically heat map, and you'll get a two-dimensional plot out of this. When instead of plotting these values out of the plane, you show it with a color. So the brighter represents the heavier thing, and more power, etc. So as you can see here, I will clear the pen marking. So this is what we were referring to as the spectrum, and this is what is the short time Fourier transform. So same thing you plot as a time progresses in small windows. So that will give this, and wherever you get a high frequency, you see a blob like this. Okay.
So this left side power plot is at what time? Like whole signal.
Yeah, whole like it is dynamic, but as of now we can think at one time point. Let's say at some time point you can always get a spectrum like this. Okay. So
oh, nice.
yeah, so I just want to show some real time. If I'll take another 5 minutes. So I'll just, okay, give me 2 minutes. Yeah, no, this is okay, this will take. So we'll do a small music demo, and I'll just mirror my phone so that I found a way to do this. Yeah. Okay. So I'll just share my this camera. Where is this? Yeah, 1 second. Can you all see this spectrogram kind of thing on my screen? Yeah, okay. So I'll just play some notes on 1 second. Yeah. Wait, 2 minutes. Okay, I'll just show this way so that, yeah. What is happening to this? Okay, I'll keep something here so that it will stay floating. Okay, now it's fine. So yeah, so I'll play Sarigama Pa so that you can see things going nicely up and down. So we'll create one mountain. So we know that